Hi. Hi everyone, thank you for attending. So we're going to talk about BPF again. So many of you probably know that we can somewhat trace many things on Linux with BPF. I want to talk about how to try and understand what may go wrong with those BPF programs themselves. So not trying to try something else, but just the BPF programs. So I'm Quentin. I've been working with BPF over the last 4 years or so. First in a company called Sixwind doing software acceleration for packet processing for networks. Then at Metronome, where I worked on hardware offload of BPF packet processing. So with all of that, you may find that some of the examples are slightly more focused on BPF for network processing rather than tracing, but everything I will present should be the same for the different use cases. So BPF is the extended version of Berkeley packet filter. You could use it to write your own programs, for example, in C code, and then compile them into eBPF bytecode and inject that into the kernel where it is verified in order to make sure that the programs are safe and that they terminate in order to avoid security issues or crashing your kernel, this kind of small issues you want to avoid. So you have an interpreter in the kernel. You also have a JIT compiler to get better performance with BPF programs. And once they are loaded in the kernel, you can attach them to one of the existing hooks. So for example, network processing or tracing hooks. So yeah, that's about it. So the instructions are 64-bit. You have 11 registers, 500 byte stack. It's not ring complete in the sense that we don't have generic loops. Now we have bounded loops. And it comes also with a number of additional features. We have maps that are shared between BPF program in the kernel and user space or several BPF programs. We have some functions we can call from the kernel. We have BTF, on which I'll come back later. So that's about it for BPF. The following diagram can summarize workflow. So we compile our C program into eBPF instructions that we inject into the kernel. It may or may not be JIT compiled. And at some point, we'll attach it to a hook where it's run when the event occurs. So where the function that we want to trace is triggered, for example. So the rest of the presentation will be organized like this. That's better. So reminder of eBPF, that's done. The tools to inspect BPF objects. So we have a number of them. I would like to introduce them in the first part for the different steps of that diagram I just showed before. And then in a second part, I'd like to make a somewhat deeper introduction to BPF tool, which is used a lot to try to get some information about the objects, the BPF objects loaded in the system. So that would be programs and maps, for example. I would like also to give a brief overview of the possible next steps in terms of BPF introspection and debugging, what's being discussed at the moment in the community and what we could do. So I just forgot to mention the main use cases for BPF. So we have networking, tracing. We have also some use case for socket filtering between C groups. There is work in progress for Linux security module. And we have also more use cases, smaller ones that exist today, and probably some others that will appear in the future. So let's start with the first step of our workflow. When I try to compile a C program, for example, into eBPF bytecode, at that step of the process, I want to make sure that the eBPF bytecode is consistent with the program I had in mind, with what I wanted to create. And so how can I do that? So I have this Clang command line, because you compile your C into BPF with Clang and LLVM. There is also a GCC backend now, but it's not as complete as Clang. And once I have my object file, I can use LLVM objdump to dump the bytecode of the program. So that's what we have here. B7, and the rest of zeros is putting the value 0 into register 0, which is used for storing the return value of the program. And then I have a second instruction which says exit and return from the program. So return 0, basically. I can also get the C source code in that output if I were to provide the -t flag to Clang and use the different options with LLVM option. So that's useful to check what I have in my object file. I have an option also that might be useful, which is instead of compiling directly from C into BPF bytecode, I can compile into assembly, BPF assembly, and that gives me an assembly file, a .s file, that is much easier to edit if I want to change my BPF code itself without having to write all the code by hand. And if I want to test a specific sequence of instructions to test some kernel BPF feature, to test, for example, for hardware flows, we wanted to make sure that some instruction sequences were processed in a particular way, so that's useful. And Clang, again, can compile this assembly into regular BPF. So that's it for the first step. There's not much to debug really at this point. That's mostly to inspect things. That's also the case when you try to load your program. So you have your BPF bytecode and you're trying to mostly pass the verifier that's something here in the kernel acting as a guardian somehow, and that often tells you, no, this I don't want of it. There is a security risk, so you have to change your program. So we want the program to pass the verifier, or at least we want to understand why it's rejected, which is essentially improving the program to get something that works. So we have a variety of resources that can be used to inject the program into the kernel and possibly get this output information from the verifier, the debug information that the verifier sends back. So there is libbpf, which is in particular used in BPF tool, which is a command line utility. For networking, we have IPTC, BCC, but BCC is mostly used with tracing use cases, tracing programs. So we can load programs with those tools without having to re-implement everything ourselves and use and call manually the BPF system call. And we can do some additional management of the BPF programs and maps. So we have different things that can give us some information. We have the logs from the verifier. We have kernel logs sometimes for some specific BPF errors. For networking, we can have netlink exstack messages from IP or TC, for example. And we have some places where we have documentation to understand those errors. So typically that would be the filter.txt documentation file in the kernel documentation, or the CDM guide about BPF, which is really complete. So this is a non-exhaustive list of what the verifier tries to check. So if you have not valid BPF syntax, it will be rejected. Too many instructions, more than the kernel supports, it will be rejected, and so on and so forth. So just so that you can have a look at an example error message from the verifier. So I'm trying to inject a program here, and I'm trying to read a packet, a network packet, but I haven't checked that the offset inside that packet is a safe offset, in the term that my packet is big enough for me to try and access the given offset in the packet. So I have a potential risk of out-of-bound access, which may never happen, because if I'm trying that on the second byte of the packet, I never have out-of-bound access, because my packet will always have a MAC header. So I virtually have no risk, but the verifier doesn't care. If logically there is a risk of out-of-bound access, the program is rejected. So the message is very useful when you know what you're talking about, BPF context, invalid BPF context access. But for newcomers especially, that's very cryptic messages. It's very hard to understand what it refers to. So we would like to have some better things in the future, maybe some additional documentation or FAQs that would tell us where to look in that case. But still, we do want to have those messages, so it's especially important to be able to print them into the console, or you're just on your own to understand what's going on. So we have some debug flags that can be passed to the tools, to the various tools. So you have to provide, for example, if you were to inject all on your own your program with a custom management program coding the BPF system call yourself, you would have to be careful to pass a buffer to the kernel too, so that the kernel can write into this buffer the logs that correspond to that message we saw just before. Because we have a number of tools already, such as BPF tool and libBPF, which is used in BPF tool, such low-level buffer management is already done for us to some extent. But for example, libBPF itself does have an additional number of debug information too. So that might be information about, hey, now I'm trying to inject a program in the kernel, or before that, hey, now I'm trying to perform elf relocation about some stuff from a given section of your object file that I'm trying to put back to the correct place into the rest of the BPF instructions. We have a number of elf magic stuff that's happening before injecting the program. So you may have to tell libBPF to dump this information. So for BPF tool, for example, you can have information from libBPF and from the kernel with a --debug option. So that's something useful to know too. So for interpreting this information, we have that's the same locations that I mentioned earlier, the filter.txt documentation, the Cilium guide. There is also some additional information now on the documentation / networking, I think, / BPF, although it's still not perfect, I think. The hardcore solution, if you don't get anything better, is to go and read the kernel code. Yeah, that's not really ideal too. So yeah, maybe in the future we'll have something a bit more user-friendly. That would be nice to have. Sorry about that. So now we have managed somehow to fix our program and to pass the verifier based on the output. We managed to make it work, to add the check that was missing for the packet access. So the program is now loaded in the kernel. It's not attached yet. It can be attached. It's just here in the kernel. It's referenced by something in user space so that it doesn't get wiped out from the kernel. So that can be a file descriptor typically. Or when the program gets attached, then it's referenced in the kernel until we detach it. So we have our program sitting here, and what can we do with it? So we have a number of options, such as listing existing programs in the kernel and maps, and dumping the instructions for those programs or the content of those maps. So maps will typically be array maps or hash maps, or there are a number of additional maps for some specific use cases. So BPF tool here is the main tool that we use on a daily basis to inspect those objects when they are loaded in the kernel. I'll come back to BPF tool later, though. I'll just move on to something else, which is BTF for BPF. Sorry, for BPF type format. So since kernel 4.18, I think, so that's recent, BTF objects can be used to embed some debug information about the BPF programs and maps. So it's something that's similar to the dwarf format that's being used with GDB, for example. So you have a number of information that are stored into your object file and that are passed down to the kernel when you inject your program, which means that the kernel may have some information about the BPF programs or maps. So for programs, it's just a matter of using a recent enough version of Clang and LLVM and passing the debug flag. for maths, we have to do some wrapping in the source code. So what I have here is classic definition of my BPF map that would be in the C source code. And I have above that to add some information, in particular about the type for the key, which is a pointer to an int, and the type for the value, which is a point to that struct. There are more details, sadly, just mostly in the commit log of that change for now. The reference for seeing how those things work would be the samples and self-tests in the kernel repository for now. We're still waiting for documentation to catch up. So an example of a program that's being dumped with a BTF format, I have the, sorry, didn't want to click. I have the regular BPF bytecode instructions here and below, and in the middle of that, I have the C instructions. I hope you can read, hopefully somewhat. So here I have an int balancer ingress, which is the name of the function. Here I have if data plus offset is superior to data end, then, and my program goes on. So this is the C instructions that were used to compile the program into BPF bytecode. But I get this information from the kernel now because the kernel knows this information about the program. So that's useful to understand what's going on. And it's also being used for some other BPF features in the sense that BTF objects like this are checked by the kernel, especially for maths. They are checked for consistency so that you cannot just load anything, any information you like to, but something that really corresponds to the map that's being loaded. And some advanced BPF features rely on BTF objects to work, but that's something different. So let's just think of it as debugging information available to us for now. So I have had the possibility to inspect my objects in the kernel, and that's good. I have my programs loaded now. I want to run them maybe. So I want to do some actual work with my programs, some processing, some tracing, whatever. So I attach them to one of the hooks in the kernel. So for tracing, that would be trace points or K probes. For networking, that would be TC hooks or XDP at the driver level. And for the other use cases, that's something different still. But how can I understand why my program doesn't work as I expected? I mean, I've attached my program to an interface and it doesn't drop the packets I wanted it to drop, or it doesn't give me the arguments of the function I was expected to trace. So what's happening? We have a number of solutions. We don't have a step-by-step debugger yet. So it's mostly, again, about introspection. We do have a printf-like thing, because we're in kernel, it's more printk-like thing. It's a function that can be called from the BPF programs themselves. So it's just when you're debugging a program with printfs everywhere, that's same thing. Except it doesn't print to the console because it runs in the kernel. So it goes to a CSFS file or pipe. You have two files actually that can be used. And you get the output of whatever information you feed to your program. So you have to use a constant string at the first argument, but that's pretty much the same thing as other printf functions otherwise. So in that case, I'm printing the four first bytes of packets. So I pass the format string, the size of the format string, and then the data that I want to use for person X here. So that's good for debugging, for understanding what's going on. That's not good in terms of performance. So we have a different mechanism which is a bit more complex to use, perf event arrays, but that can be used to stream data more efficiently from the kernel to user space. So that's what you would use, for example, if you were to re-implement TCP dump, but with BPF programs attached to XDP interface, you would stream data with perf event arrays, or you could use that to send the flow of data, like for tracing each time a system call is called, and you want to print the arguments for that system call. That's also possible to use perf event arrays to notify the user space, and user space can print them into the console. So you could have something that's close to a trace, at least in appearance, you would have something somewhat similar. So yeah, and one of the advantage of this is that it can be used with a hardware offload for network processing too. So one thing that's interesting too is that BPF can be used for tracing, right? So why don't we reuse BPF for tracing BPF programs? Well, actually that's possible now. Since the latest Linux version, I'm not even sure it's out 5.5. I think it's being it's the merge window right now. So we do have a possibility to attach BPF programs at the entry or the exit of another BPF programs, at least for networking programs. I'm not sure it works with tracing programs. So at least for networking programs.
It's in 5.5 and it doesn't.
Okay, so it doesn't. But for networking programs, that it's supposed to work. So you can have the input packet, the data of the packet you are processing with the program you are debugging, and you can also get the output data, so you can check the difference between the two and see how your program managed to process the packet. You can also use BCC or BPF trace to inject programs to trace the kernel if you are hitting some unknown issue that's happening. For example, during verification time, I've been using BPF trace a couple of times to understand what was the function inside the kernel verifier that was rejecting my programs. So it can be useful to some extent, but that's not the easiest way to understand what's going on. But still, that's something good to think about if you're stuck otherwise. So we have a feature that can help us testing BPF programs. And by testing in test runs, I mean instead of attaching a program to a network interface and wait for packets, what I do is manually tell the system to run this program, not on a real packet, but on that input buffer, and to give me back the output data once the program has run. So there is a specific program type for that. That can be, no, that's not a program type, sorry. That's a subcommand for the BPF system call. And that works best, again, with networking program because it's a bit more tricky to use with tracing programs. So you provide input, you get output, and you can see what's happening. It has some limitations, so not all program types. For tracing, it's a bit difficult to check how kernel data structures that might be changed by the program are changed or not. So it's a bit more complicated to implement. Some BPF helpers are, so those functions that you can call from within BPF programs are very hard to support in that, with that mechanism. For example, when you try to redirect a packet to a different interface, how can you check that it really worked just by getting an output buffer? That's another issue. And we would like, well, some people at least would like to have this feature available for non-root users in order to run test suites on BPF programs, but there are security issues again. So yeah. So a number of these limitations have been proposed in a conference in March, NetDev conference, for discussion. So things might evolve and improve, hopefully. Another thing that might be useful for understanding what's going on is that you have statistics now regarding programs. So you have to activate them with syscontrol, and then you get the duration of your program run and the number of times the program has run. So at least you can check that your program has run the number of times you expected it to run. It's not enabled by default because there is a slight overhead for gathering statistics when you run the program, so you have to activate it. Small number of machine learners, things to know about debugging at runtime too. So perf has support for annotating BPF programs. So you can run perf top and go to the annotated part, and you can find the instructions of your program on which the CPU is spending some time. So who knows, if you need to check what's happening on that side, you're being covered. There are a number of user space BPF machines, so they are nowhere as complete as what's in the kernel, but still, if you wanted to run a BPF machine under GDB, today you will have to turn to one of those user space machines. So UBPF especially is in C, or BPF is in Rust, but otherwise they're pretty equivalent. There is a small debugger tool. I think it's step by step. I don't remember. It's a debugger tool, but it's for legacy CBPF, which is much simpler than eBPF, so also simpler to debug. And that's under the kernel repository. So that's about it for loading and running BPF programs. I just wanted to speak quickly about writing programs in user space to manage your BPF objects. So, so what we want is the ability to debug such programs to improve BPF support in the toolchain in general. So we have the ability to use those frameworks that work already, BCC, BPF trace, libcfe as a library I've been working for, and that turns some filtering rules into BPF programs, network filtering rules into BPF programs. You have libbpf, of course, that can be used to implement your programs managing BPF objects. You have a feature that allows you to dump the list of BPF-related features on your system with BPF tools, so that you can check what's available, what program types are available, what map types are available, what BPF helpers even, and if the BPF syscall in the first place is supported, these kind of things. Since it's a debugging tool anyway, we have support for BPF in strace. We have BPF support in Valgrind, although in Valgrind I think it might be getting a bit outdated. But strace I think is mostly up to date. So that's really nice to have, especially when you're trying to inject a program into the kernel and you don't get much information, you just get an error code. And it turns out that your BPF tool program has been trying several different things, like checking that basically I can inject a very simple program, and then it tried to create a map, and then at last it tried to inject your program. So which of those different codes failed, I'm not really sure, so I can trace it with a trace. That's very useful. So that's it about the introspection, debugging BPF in general. I wanted to talk a bit more about BPF tool, because that's really a useful tool to do all those things. Not all of them, but most of them. So one of the, I hope you can read at the back of the room, one of the simplest function is listing the programs that are running on the system. So I have BPF tool prog show. So this is a list of programs attached to socket and in C groups. So those first 7 programs had actually been loaded by systemd on my system for firewalling things. And then at the end there is one program that I had added to, but XDP, so networking processing. I can list those programs. I can also dump the instructions, so I can dump the what we call the translated instructions. That's after my program has been loaded into the kernel. Kernel verifies the program and does a number of rewrites. And because of that, there are some small changes, possibly not in terms of the logics of the program, but just in terms of small offsets regarding to the different data structures being used. So I can have just these instructions as they are in the program, but I can also dump the JITted instructions. So in the second case, it was JIT compiled into a native binary for x86, and I can get all those instructions. So that's interesting to see what's happening with the JIT compiler. I can load the program. I can attach it to a variety of hooks. I don't think I can attach it to kprobes or trace points with BPF tool at this time. So I have the related commands: BPF tool prog load, BPF tool prog attach, C group attach, and for networking that would be net attach. Yeah. I can work with maps too, so I have BPF tool map show to list the maps. All those LPM try were related to the systemd programs injected into my system. I can look up entries in maps. So here's a case of a very simple array map, and I'm dumping the content of the first entry. So what we don't have here is BTF, which is missing. With BTF information, I would have more data than this. I forgot to put the picture. I would have the fields of my entry. So my entry here is comes from a C struct with a number of fields of attributes, and I would have the name of the attributes and the values beside them instead of just a blob of hexadecimal values. So I can dump the full map at once too. I can update an entry in the map or delete an entry in the map too. It even works for some specific, more specific map types, such as the one used for jumping from one program into another one. You have these kind of features, and BPF tool is really helpful to just update the map. I'm sorry, this picture is really small. I'm not sure why. So the idea is what I presented earlier. Can I zoom on that? I don't know how to zoom on that. I'm sorry. So it shows a list of BPF features supported on the system. So first one is BPF syscall for unprivileged users is enabled on that system. JIT compiler is disabled, and so on and so forth. We have a number of BPF-related config options that were used when compiling the kernel, so that we know what BPF features will be available, and all that can be reused when you write user space programs working with BPF stuff. Yeah. So this is not too big, but not as small. Picture of BPF prog runs. So what I'm doing here is just running a test run of a program I've loaded previously into the kernel. So I have BPF tool prog run. This is a handle to my program. I'm providing input data in, and my input file, data out, and dash to tell it to dump into the console. And I want to run that program 10 times. So I get here the output data. Hello Twitter, that was because I wanted to put that in a tweet. Return value of the program is 0, and I have the duration on average of those 10 runs. So here it is for test runs. So some additional features for BPF tool without any screenshots because they're too small anyway. So we can list programs per C group, per network interface to per tracing hook. So we can really inspect at that tracing hook, what do I have? We can load several programs at once, especially useful when you have a number of programs with what we call tail calls, and you jump from one into the other one. We can dump directly into the console the output of BPF trace print K. We can dump from perf event maps. There's a thing about generation of a skeleton header file for helping with writing programs for managing BPF objects, but that's pretty new. We have batch mode, we have JSON support, which is pretty nice. bash completion and more. So I had made a Twitter thread if you want to look into that. More information, obviously, there is some documentation for BPF tool at least. We have man BPF tool and different man pages for the different subcommands. So BPF tool prog, BPF tool map, and so on. So here you are ready to use BPF tool now. It's being packaged now on Fedora and Ubuntu too on the latest ones. I think it should be added to 1804 sometime. Otherwise, BPF tool is located under the kernel repository. Few words about what's coming next for BPF debugging. So we want to add more stuff to debug, like can we have more modular programs with more modular calls between programs. So there is something that was added very recently to the kernel for having that. Could that help for debug? Maybe. There is a discussion about adding more information to the sysfs system file, and also discussion about improvements for the test run feature. It will be really, really so nice to have a real step-by-step debugger for BPF. We don't have that at the moment, but people are really thinking into that. So how can we do that? Should we? Sorry? Why Bitrace? Where is Bitrace? I don't know Bitrace enough to know if that would work. But that's an idea maybe. So we have a. Yeah, we should talk about that. So here are some ideas that were proposed besides Bitrace. Running a program in a VM, freezing and freezing it, is that doable? Extend the BPF prog test run interface, attach kprobes to every single instruction. Is that something doable? That's just leads to explore for now. I would like at least have an updated documentation because what's existing is not always up to date, and I definitely think we would beneficiate from a real troubleshooting guide that would tell you this error is often related to that thing in your source code that you should change to that other thing. So again, in particular, the things about step-by-step debugging and sysfs are being proposed to the next NetDev conference in March. So to conclude, debugging BPF programs is not trivial. We don't have a step-by-step debugger yet, but the tooling is getting better and better. We have more tool, more efficient. We can dump instructions and map contents at any stage of the workflow. We can print data when the program's running. We can do test runs in the kernel. We can run in user space BPF VMs. That's not the best we can do, but that can help debugging what's happening. BPF itself can be used to inspect other programs, which is really nice. We have should have added here the BTF debug info format that's being used to provide more information. So all of this it's here. It's already very good, and hopefully we will have better things in the future too. So fingers crossed. And that's it for my presentation. Thank you. So I don't know if you have time for questions.
Yes.
Quick. Okay, so yeah.
So if I want to generate BPF bytecode by myself without just writing a C program, can I do this? And what is the best API to do?
You can, if you want to generate it yourself. So the question is.
Bytecode, BPF assembler program essentially.
So if you want to code your own BPF assembler program, you can do that. You might hit a number of issues, not on basic program. It will work for basic programs, not using advanced features. But if you're trying to use BTF debug information, for example, or more advanced calls from one program to the other one, there is a number of things that are happening when I mentioned health relocation stuff. And this is getting more and more complex. So you could re-implement that, but that would not be trivial. So libbpf is really a reference here. It doesn't prevent you to work on your side with another BPF assembler, but for more complex stuff, you will have more work to do and more time to spend on that. Other questions? Yes.
Possible to handle an hardware interrupt from a BPF?
Sorry, can you speak louder?
Possible to handle an hardware interrupt from a BPF program?
Is it possible to manage a hardware interrupt from BPF program? I don't think so. I'm not sure. I don't think so. You don't have a hook on that, I think. So I would say no. There was another question at the back. Yeah. I'm sorry. Can you speak louder or come over here, please? Last question. Yeah.
How big average available BPF program has? So is it
Yeah. So how big is a network programming BPF? Is a network BPF program on average? It was limited to 4K instructions before. Now it's limited to up to 1 million instructions, but that's not really true because there's a number of instructions that the verifier can check, and it checks some instructions several times. And so the average, it's hard to tell because it depends on what you're running, but the 4K limitations was definitely a hard limit to some people, and they wanted to have more than that. That's also why you can jump from one program to another one. One motivation was to circumvent that limitation. So I don't have a number in mind, but programs can range to a few dozen instructions to thousands and thousands of instructions now. So it really depends on the complexity of your programs. You're welcome.